Can you hear me now? Yes, I can hear myself. So I was saying that I'm going to give a little outline of what I want to discuss, but I would say that the second part is a backup plan in case I had too little. Then I can go into it, but otherwise I'll focus on the first part. But let me put an outline of what I would like to say. Some things that I think. Can you read my handwriting, or is it too small in the back? It's too small? It's good. You guys have good eyes, because sometimes when I go back, I cannot read my own handwriting. That's why I ask. But the outline is basically I have part A and part B. Part B is a backup. In case I try not to go too fast, maybe try to find the right pace. In part A, I would like to talk about problem in 1D. In part D, I jump to 3D, skipping 2D. So I want to talk about some physics related to SU2 as you go to SUN, but indeed, I will go only as far as n equals to 3. Not very large n. It gets very complicated. So I would like to discuss a little bit about the 1D repulsive Fermi gas. And I want to say something up front. Most of the things that I'm going to talk about and discuss, they have no connections with experiments. There are no experiments that I know have succeeded in doing this, so it's going to be in the realm of dreams. And the conditions to have some of the things that I think are open or perhaps interesting are not so easy sometimes to satisfy. We learned already from Ivan and others that once you start putting more fermions with more internal degrees of freedom, life gets very miserable and very difficult. So you have to make some assumptions which may not be seen in real experiments, although there's some hope with the beginning work of Nirnavon at Yale, in which he's starting to put some 3 internal state fermions in a box, and maybe there's a chance that not all hell breaks loose in a box. And maybe some reductions of the 3-body losses coming up that you see normally. But anyway, this is, so basically everything that I'm going to be talking about here, unfortunately, I cannot say that I'm trying to explain an experiment. I'm trying to think about things which are interesting to me and hoping that someday they can happen in experiments. So in some sense, it's a little bit more of a dreamland than explanations of experiments. So the part A is what I'd like to discuss about is about the 1D repulsive Fermi gas with some specific interaction that I'm going to tell you about. But I want to add a twist. I want to add what happened if I have spin-orbit coupling added to my system. And then ponder a little bit about SU2 and what may happen on SU3. And I'll try to motivate a little bit why. And then, as a backup plan, in case usually one topic is enough, but sometimes I'm afraid it's not enough. So I have a backup plan. If I go too fast, then I will have some time to say something about the 3D. So I'll change the dimension, and I'll change the sign of the interaction. And I want to talk about 3D attractive Fermi gas. Again, with spin-orbit coupling. Then maybe say something a little bit about SU2 and SU3. Okay, so this is the backup plan in case. I'll go a little bit fast. Okay, so the one important thing that I want to talk about, since in many cases when we talk about SU3 systems, we always think about somehow quarks, at least I always think about quarks. I want to make some connections to particle physics. I mean, we have seen a lot of connections between cold atoms in condensed matter physics and so on. So I want to add just a little bit more flavor and say, look, we can connect to some other things also, which people have studied in particle physics. And we have our own stuff, which can have particle physics sounding like names, but they refer to some physics which is related, but also different. So with that, then I just want to just give you an idea where the n will come, n equals to 3 will come. We know that in the standard model, we have 12 fermions. And they all, now we know that they all spin 1/2 and massive. The neutrinos were the ones that initially, there was hope that the neutrinos were massless, and for a while they thought to be Weil fermions. But now we have some evidence that there is at least some bounds that indicate that the mass of neutrinos is non-zero, and therefore they're most likely Dirac fermions. So why I want to do this, just to remind you, so then 12 fermions, of course, 6 of those are quarks. And that's what we get some inspiration for SU3 from Gelman. And we have 5 bosons, four of which are vector bosons. And one is a scalar. The scalar one made head waves more recently, the Higgs. And the other ones made head waves in their time. Photons, gluons, the W boson and the Z boson. And of course, when we're thinking about fermions in condensed matter physics, most of the time, not always, but many aspects of condensed matter physics, we always tend to think more about fermions. Electrons are fermions. Sometimes you create excitons, which are bosonic-like. We look at those things also. But a lot of things having to do with electrons, we're thinking about fermions most of the time. And of course, they're spin 1/2. So I didn't say about the other 6 of fermions are quark, and other 6 fermions are leptons. And that means it includes the electron, the muon, the tauon, and the neutrinos associated with each one of these particles. So the leptons that we like the most in condensed matter physics is the electron, so it's Cm. And for the electron in condensed matter physics, of course, it's a spin 1/2. A lot of work has been done in trying to find Majorana, Dirac, and Weil fermion physics. In some cases, I think the experiments on Majorana some of them have been recanted, so the observation by the Dutch group seems not to, after the review, it seems not to indicate that they really found the Majorana fermion or Majorana zero-mode states. And so one of the interesting things, of course, that if you have massive fermions, they would either be Majorana or Dirac. But if you have massless fermions, you have Weil. And Weil has another interesting aspect to it, which is that they're helical. They have some chirality. And the massive Dirac and Majorana, the difference, of course, is that in the Majorana case, the particle its own antiparticle. Okay, why am I talking about this? I'm talking about this because I think at least in the SU2 case, you can make a little connection to systems in 1D. By using the bosonization technique, you can transform fermions into bosons. And if you have spins, there will be pseudo-spin 1/2 bosons. And the question is, when you look at the excitations that you can find in those systems, what kind of properties they have. And one of the natural things of the low-lying energy modes, they'll be massless. The question is, can they be helical? So there'll be the version of Weil fermions into, called helical bosons. If you want to be gracious to Weil, maybe call it the Weil bosons, I don't know. But you have some additional structure that emerges on that. And of course, we know already when you're thinking about Higgs, in connection to condensed matter physics or cold atoms, you can think about systems that have broken symmetry. You can have low-lying, continuous broken symmetry, low-lying excitations, which are then Goldstone modes, bosonic-like. And you can have Higgs-like excitations in principle. Sometimes they decay and not easy to observe. But you have these emergent bosonic degrees of freedom that connect also indirectly to particle physics once you have a continuously broken symmetry. So I'm staging that because in the particular case of spin-orbit coupling, if I add spin-orbit coupling to the one-dimensional interacting Fermi gas, spin-orbit coupling can do some strange things. And one of them is introduce some helicity into the system. So the question then arises, if you have, let's say, SU2 system, and you add spin-orbit coupling into the system, what happens to the spin and charge? Well, the most natural thing to think about, what's going to happen? By the way, you can ask any questions anytime. Feel free to interrupt if you like. But I will also ask questions. So what happens? If I have a 1D gas, pick up your favorite potential, let's say the Coulomb repulsive potential, and you say, okay, we can just work Tomonaga-Lachlan liquid model and find out that spin and charge separate. It's a peculiarity of 1D. So when you add spin-orbit coupling, you're coupling the center of mass degrees of freedom with the spin, essentially introducing a coupling between the spin and charge. And the question is, how interesting this coupling is. So what I would like to do first is to sort of talk a little bit about the 1D Fermi gas in the context in which I have, of course, a kinetic energy term plus an interaction term. And I'm going to choose a specific form of interaction, but many of the things do not depend in gory details of the interactions, particularly spin-charge separation. You have to satisfy a few conditions, but and then the type of interaction that I'm going to be looking at will be, well, first write the kinetic energy with no spin-orbit coupling. So remind you of some general results, which have been known for many years, I guess. So the kinetic energy pictorially, I can just write down, if I have no spin-orbit coupling, I have degenerate spin states, I have two, let's say, parabolic bands with states up and down, which are degenerate. So my kinetic energy, let's say in first quantization, I'll write second quantization, or I can write in second quantization, doesn't matter. If I have a chemical potential, and please, yeah, I'm including the chemical potential on the kinetic energy, so grand canonical stuff, but so I can say, well, my kinetic energy with respect to the chemical potential of the system is going to involve free particles or independent particles with a parabolic band. S is the spin, K is the momentum, and that's energy with respect to the chemical potential. So if I have a chemical potential which is lying somewhere here, I'm going to have Fermi points which emerge, and there are 4 of them. They're degenerate 2 by 2, and then I can have an interaction V, which is, in my specific case, or I can write in real space, but I'll write in real and K space, which is going to be some integral or double integral over position. I'm going to call X and Y here just for involving a particle or density type of interaction involving particle at position X with spin up, some potential that depends on the separation between them. I guess I can put the absolute value here of this thing. And I'm going to consider the case of interactions only between up and down. Of course, in the Coulomb problem, we're going to have direct interactions between the up and down components because it's a purely density. So this one here, I'm going to choose to be explicitly SU2 invariant. So only the up and down components see each other. Just by construction, I can do the same thing with the Coulomb problem, but I want to mention that out. And this interaction could have a range, could be 0 range, but I'm going to keep a range first because I want to take this limit at the end only. And I can say that this interaction depends only on the separation of particles, and have a structure which has an overall factor in the front which sets the interaction scale, and some function which depends on the separation of the 2 particles. And that function can have a range, or not. It can be infinitely range, can be Coulomb, could be something that decays fast. And the assumptions for getting some of the results will come as we specify in more detail what that is. So let me just move this up. Okay, so if we do this and we ask ourselves the question, that already goes back to Tomonaga, Lattinger, then Haldane also in the 80s. And then, of course, you can find those things in textbooks. One way that we can try to look at those things is take advantage of a peculiarity of 1D systems that if I'm interested in the very low energy physics, and I have a chemical potential here and low temperatures and so on, I can find these Fermi points. The low energy physics is expected to matter only nearby these Fermi points. So what one generally does is to linearize the kinetic energy operator near the Fermi points with the hope to try to find out what are the excitations that you have in the system. And that is done using the bosonization method. So basically you define your density operators. When you do this, you basically have right-going fermions and left-going fermions, since you are in one dimension. And you can define density operators. R here is the right or left. And for each momentum Q and each spin S, so S can be up or down. And the operators, of course, in momentum space, I already write in momentum space to save some time, sum over k of the fermions that are now specifying right or left, k plus q s cr k s. And once I do the expansion and linearize around the Fermi energy, my kinetic energy acquires a simple form. So I have to sum over the right and left going fermions, sum of the k states within a certain momentum width. I'm always going to be assuming here that it's momentum width. Maybe I can put a prime just to indicate that, but I want for notational. Then you expand that, and when you expand, of course, you get something which looks like linear in K, and then, of course, I can write this down as being, I'll explicitly just write the up and down separately, R, K up. Of course, in this case, the velocities are the same because there's no difference between up and down in this case. And then I can have a second term which is identical, except that I change the labels of the fermions, the spin labels of the fermions, from up to down. Okay, so then we use this property of the linearity of those things and can define operators which are bosonic operators. And that only works in 1D and works because of the linear dispersion that you have. So I can define Bose operators. I'm going to just define a few here, which are related to this right and left density operators. And I'll just give a couple of those. It's only what I need for now. So rho L minus QS for Q positive. And you can do the same for the right-going fermions, so I'm not going to write this. And so and once you define these operators, then the bosons defined that way, plus the right ones that I didn't explicitly show, they obey bosonic commutation relations. I'll write them all also. These are the most important ones. And of course, for bosons without the dagger, they completely commute. So B dagger, and B commute. And then, using this mapping that basically only works in 1D, and when you have linear, so it's a very specific thing, you can map the fermionic Hamiltonian in the linear, with the linearization, can be mapped into a bosonic Hamiltonian for the kinetic energy, which is given by the sum over Q, again restricted to small Q the F absolute value of Q, bosons QS, QS. So in the case where those assumptions are valid, we know how to map the kinetic energy fermionic description into a bosonic description where the bosonic particles have a linear dispersion and a velocity which is identical to the Fermi energy. Okay, then I go to the next thing and say, well, now what we're going to do is I want to do something with the interactions. So I add interactions to back to my problem, which is somewhere up there, and I'm going to write this interaction in momentum space, because I'm going to be working in momentum space all the time. I could go to real space, but if I try to do SU3 in real space, it's a nightmare. So I'm going to work in momentum space. And I mentioned something about the SU3 as an open question at the end. So if you look at the interaction that I wrote in real space, that interaction can be written in momentum space as some V0 that sets the scale of the strength of the interaction, sum over Q of rho, the density Q for particles spin up, times the density for particles spin down, times a function F Q, which is essentially the Fourier transform of F. Maybe I should put a tilde here. FQ is a Fourier transform of f x, y. So that's going to be important, of course, because we're going to make some approximations in terms of what the interactions are going to show up that we're going to keep to get the spin charge separation as done in textbooks, so nothing super special. So then, of course, what we have succeeded in doing effectively is that to say, okay, now these rows are like this, so I can write these rows in terms of the B's, or the B's in terms of the rows. That means that I can write my interaction also in terms of the B's that I define. So this means the interaction that I have can be written in terms of the boson operators defined. And the interesting thing about this is that this is bilinear in the B's. This will also be bilinear in the B's. So what I have to do, I have a quadratic Hamiltonian in my bosonic operators. So what's the next step? If I need to, I'll do a Bogoliubov transformation. So it becomes a very simple problem. Of course, this was done back in the 60s up to 80s. A lot of stuff was done. So the important point is that you can write the V's in terms of the B's. V is a bilinear of the B's. So I should not put this, I put this. So which means B dagger B can show up, B dagger can show up, BB can show up, and B dagger can show up. It's a bilinear. Well, Bogoliubov taught us back in 1947 how to do this. And that's the beauty of this mapping, because things go very simple. Then we're going to complicate. We always say that life should always be simple, but it never is. So we're going to complicate. So that's the case, and then, so I'm not going to go into all those details, but it's a bilinear, so it means that when I combine the kinetic energy, which is also bilinear, and interaction, which is bilinear, I can find when it exists, right? So mathematically, sometimes it doesn't exist because of parameters are such that conspire that the Bogoliubov transformation doesn't hold. But when it exists, I can diagonalize it. So that is, you can, if the eigenvalues are real and so on, right? But sometimes they're not. Okay, so I can diagonalize it. So I can move this up. And And if I do that, my H is going to be, even just to be sure, when did we start? 11:35. So I already half an hour, so it's long. Okay, so it seems to be this okay. Sounds good. I just want to pace myself because I have some time in mind. Thank you. So this means that, and if I follow the standard procedure, I'm going to find that I can diagonalize that bilinear Hamiltonian and two modes emerge. B2. Okay, and two modes emerge. Then, of course, and I don't want to give you the direct expression, but these two excitation energies, these velocities, will be functions both of the Fermi energy and my interaction parameter, V0 or potentially the range and so on. So it depends on the V0s. And most of the time, when we get to this point, the interaction has a Q dependence, which is right there, V0 times F tilde Q. And we argue, just to simplify our lives, that at the large Q momentum transfer processes are not relevant, either in the renormalization group sense, or if you just have a Coulomb interaction or sufficiently long range interaction, the large Q processes are strongly suppressed in comparison to the small Q scattering processes. So this V naught here, at the end of the day, it's transformed typically into processes which are called G4 or G2, which are basically the values. Values of the scattering processes at low Q. So this is what the interaction would give. And so the two modes that arise are, then you can almost guess what the modes are coming from. You have the Fermi points, but the two modes can be written explicitly, one of them being associated with rho of Q, which means the total one mode, let's say the mode 1 is associated to a charge density modulation. So C dagger plus Q, CKS. And the other mode can be associated with, I'm going to call it SZQ, which is going to be a sum over K, CK plus Q, S dagger, sigma Z, CK. And you find out, of course, that the way that V1 and V2 depend on the parameters, Vf, G2, and G4, is different. So this means that the velocity of V1 is different from V2. If V1 is associated with a density, so we have a type of charge density wave, the 2 is going to be associated with a spin density wave, and they propagate at different speeds. Therefore, you can say that you have spin charge separation. Okay, so this is something which is celebrated for various types of interactions. The Coulomb one is an example. For this one here, the same holds. As long as there's some range on the interaction such that you can neglect the large momentum transfers. So that holds very solidly without invoking renormalization group or anything else, just on the behavior of the interaction for large Q. Okay, then life seems to be very simple. Charge and spin are separated, they're divorced. Then I want to try to reconciliate them. So I make a phone call and say, what about spin orbit coupling? You guys can recouple. Maybe you can get something interesting out of it. Mix the spin and charge back together. And then in the process, maybe I get some interesting thing out. So
Carlos, when you say you neglect the large momentum transfer interaction, would that mean that those conclusions do not apply to content interaction, delta function interaction? Because delta function interaction can transfer arbitrarily.
Yeah. So they do not strictly apply to contact interactions, because otherwise there will be additional terms that will show up, which you may have to argue in a different way how to drop them out. Here, I have to have some range. If I don't have the range, I cannot suppress the large momentum transfer, as you pointed out. So I need it to get it at this order. Now, if you then do something more sophisticated than just bosonization, maybe you have to calculate all the contributions and see if these operators are relevant or not relevant, and that's a separate story. But for me here, I really need a range. Otherwise, I cannot drop it out. I mean, it could be sufficiently short that, my momentum stuff, but I need a range. There's no way to get out, at least at this stage. Maybe I can take the range going to 0 at the end of the calculation, but I cannot take it at the beginning. It's not going to help me. Okay, so then I say, fermions, in the first experiments on spin-orbit coupled bosons came about, I think a lot of people got excited and then immediately jumped into fermions. There was a great excitement back in 2011 or so. Of course, Jean Dalibard was one of the people that really did a lot of groundbreaking work in the late 2000s and so on. But then there was the experiment done by, I think the first one probably was the Jan Spielmann experiment. Wolfgang did a lot of beautiful experiments also on that for the bosons. And then when the bosons came along, everybody said, must be able to work with fermions. Fermions will be exciting too. So let me tell a little bit how you do this, supposedly with fermions. The sad story is that so far, the best candidates that would have, like lithium or potassium or terbium-173, I would say at least lithium and potassium. Lithium has a heating problem. You can maybe see the dispersion a little bit, but you cannot do much with it. And potassium, also very difficult to work with. So again, this is all in the realm of speculation or theoretical interest. There's no experiments. Of course, there's issue also the short-range interactions that you have to worry about. So what I'm going to be doing, again, following this kind of things, I'm curious. I want to know what happens under my assumptions, under my conditions. And let me take then what happens if I now add spin-orbit coupling to the system. And so in order to do that, I just want to give you some kind of intuition how these things happen, how this was realized in bosons. The typical idea is that you would have, and I will make it very simple. I don't want to put too many complications in my life. I imagine that I have an atom, a boson, for instance, a two-level atom, which I'm going to try to induce or introduce using lasers a spin-orbit coupling to the system. So it's a fictitious thing. It's not a real spin-orbit coupling as you would see due to relativistic corrections. It's something that you can, in principle, engineer and has been engineered for bosons. For fermions, there are some experiments people tried, but they cannot go to very low temperatures. It has been seen that they can generate the dispersions, so the spin-orbit coupling is there, but the temperatures are too high to do something beyond that. So far, I mean, Wolfgang may know more about the latest developments, but as far as I know, it's still hard. And so what I want to look at is then to say, let me have a spin state up, which I'm going to call the 0 state also, using different notations. And this is for, in the case of rubidium, but doesn't matter. So let me call this the down state, up state. I'm going to take the zeros out. And what I want to do is to use a Raman transition to, I can detune and so on, but I'll make it resonant in my case just to make life simpler also, because detuning also adds additional things. And the basic idea is that you have an atom. Let's say you are some in the up state here. You come with a photon from the left, let's say, which I'll call the first photon. And then you try to cause a transition to that excited state, and I'm going to call the down one. And once you do that, so a first photon come in, do that, and of course, if the atom absorbs the photon, what's going to happen to the atom? I'm an atom, photon comes in, gives me a kick, what do? Stay where I am. I get the momentum of the photon, and I get a kick this way. Then I get another photon coming, and I want to do it in the opposite direction. But I'm in an excited state. So the photon comes in, gives me a kick, but I'm in an excited state, which I'm here. I'm here now. So what do? I de-excite. Oh, this photon hit me. Oh, man. So, but in doing so, I stimulated emission, so I emit a photon in the other direction, and this guy comes down. As it comes down, what happens to the atom? I got one kick. What happens to the atom? Recoils, gets another kick to that direction. If I reverse the process, I can give kicks to spin up or spin down, to the right or to the left. So I have a spin-dependent process. So what happens in this case is then that the kinetic energy that I had before, I'm going to write in a matrix form now, which was simply for spin up and spin down, I just have a parabola, simple kinetic energy. But now, due to this counter-propagating Raman beams, I can give a kick to, let's say, up particles to the right, and can give a pick to down particles to the left. And that means that I can shift the momentum by a total momentum transfer, which is going to be twice the momentum carried by individual photons, a two-photon process. And at the same time, squared, sorry. At the same time, I also couple the states 1 and 2, and that gives me a Rabi coupling. So coupling between states 1 and 2 doing the same process, some random process. And this is, of course, the notation that I think is more or less standard with experimentalists. But you can also have some detuning, which I'm not going to consider. It's also interesting, but a lot of interesting physics with the detuning for bosons and so on. For fermions also would be, there's some parity things that come along. But right now, I'm not going to worry about that. But if you look at this thing, right, just a simple structure, I mean, the transitions cannot be perfect and be slightly detuned. Let's say minus delta over 2 here and delta over 2 there. So the actual detuning is causing, is presenting itself as a magnetic field also, a shift, a magnetic field, because it's different for spin up or spin down. The Rabi frequency, the Rabi coupling also presents itself as an exchange field, just couples to the spin. And of course, the KT here is just telling that the energy of these things are dependent on KT. The energy is different for spin up from spin down. So the KT, the presence of the momentum transfer, is the thing that gives you the spin-orbit coupling. So at the same time, you have spin-orbit coupling, but also kind of Zeeman-like fields coming from the detuning and from the Rabi frequency. So, of course, this is a two-level problem. So it's effectively a two-level problem, which I have spin one-half systems on an effective magnetic field. We know how to solve that very easily. But before I do that and use those things, let me just go on and bring the other table down. Monter, descendre de 1. Yeah, I think this is only one. Let me see if I speed up a little bit. Okay. So then I can just, oh, what did I do? I raised the wrong one, right? No, this is number 1. Oh, but I covered the other one. Yeah, we need the periodic boundary condition thing. But in any case, I can write it again. So what you see here is then that my Hamiltonian that is behind the thing, which I rewrite, can be written as some. And now I'm going to put the detuning to 0. Simplify as much as I can. Right? Detuning to 0. Interesting stuff on detuning, but not today. And this thing just goes. Now I'm going to use, the theorist language. I'm going to call that an external magnetic field. I'm going to call minus hx. So that's the Rabi term. And the kinetic energy here for 1 is going to look like this. Right? So it's a 2 by 2. We know exactly how to solve. But pictorially, of course, what I have done was simply this. Well, before, I had the 2 parabolic bands completely degenerate, up and down. And by introducing the EKT, what I've done, I shifted the up guys to the right a little bit. And I shifted the other ones to the left a little bit. So this were the up ones, and these are the down ones. Now I can mix those by the presence of the Rabi term, or the minus hx that I call. And what's going to happen, of course, is that the dispersion changes to something, maybe red, to something that does this if hx is sufficiently small, but if hx is sufficiently big, I'm going to have, instead of having a double minimum, I'm going to have a single minimum on the lower band. So I have 2 situations. I have this situation, and I have this situation in my problem. And that happens when hx, and I'm going to use units of the momentum transfer energy, just because I'm going to keep the momentum transfer fixed. If this is greater than 2, well, maybe hx divided by the less than 2. So if the Zeeman field is weak, I have a double well structure. If it's strong, the double well structure, the minima, the upper minimum, and the 2 minimum, the maximum and the 2 minima merge. And so I have a different qualitative situation. Well, why is that important for me? Well, it's important for me because if I can tune the chemical potential, or I can tune the density, I'm a theorist. It's not easy to do in the lab. But I want to do it. And so I can have different situations. Okay? And why I'm focusing on that single particle stuff first? Because there are different situations because depending on where the chemical potential cuts, let's say the chemical potential lies here, or the Fermi energy lies here, I have 4 Fermi points. If the chemical potential lies here, I have 2 Fermi points. And of course, if it's below the bottom of the band, no Fermi points. Interaction is repulsive. There's nothing happening there. Okay? And so then I can say, okay, now you have these Fermi points. What was essential when I talked about spin charge separation problem was I could linearize around some Fermi energy from Fermi points. Now I have here, I can have places in which I can linearize. The difference, though, is that as I change my KT, which is the spin-orbit coupling term, or I change AX for fixed interactions, what happens to the Fermi velocity? Yvonne? Remains the same? No, it changes because the spectrum is changing as a function of the spin-orbit coupling, and it changes as a function of HX. So I can play the same game as I did before for the case in which I have no spin-orbit coupling and no Zeeman field. I can diagonalize the things with bosonic methods because I can still linearize. Now, the nature of the Fermi points changes. I have 4, I have 2. When I go from 4 Fermi points to 2 Fermi points, what does that remind you of? (1960). I have a Fermi surface that had one shape. I change some parameter. I'll give a hint. Pressure, bismuth. What happens? The Fermi surface changes qualitatively. You have a neck in that case, breaks, and rearranges itself. I have 4 Fermi points. Of course, I'm in one dimension now, so it's even easier. And suddenly, as I change my parameters, in this case, like the chemical potential, or I could fix the chemical potential somewhere and change the band structure, changes with respect to the chemical potential, and I can go from 4 points to 2 points. That's a Lifshitz transition. Right? It's topological because the Fermi surface changes from one type of geometrical structure to another type of geometrical structure. So we have 4 Fermi points here to 2. I can play the same game here. It's even more interesting. I can cross. Here I have 4 Fermi points. Here I have only 2. And here I have something weird. I have 4 Fermi points again. But what's the difference between that and the original problem? Well, the Fermi velocity on this side is positive. The Fermi velocity here is negative. Positive, negative. So there's a difference in this case. Well, I'm going to focus mostly on this case, but I'm going to mention, because it's too much, I'm going to mention that stuff has important implications when I look at the excitations and the helicity of the excitations. Okay, so then the important point that I mentioned to you in the usual spin charge separation problem is that you have Fermi points and that you can linearize around the Fermi points. I have the same structure here. The difference is that my situation is much richer because I'm not going to always have 4 Fermi points. There I either have 4 Fermi points without spin-orbit coupling or 0, which is the zero density limit, which is not interesting in this case. Of course, the zero limit is interesting in other examples, not here so interesting because you have nothing, no excitations. But you remain with 4 all the time in that case. 4 Fermi points, the degenerate. Here, I can change from 4 to 2. And that makes a difference because the number of collective modes that I'm going to have will change from 2 to 1. Okay? So that's one difference because there are these Lifshitz transitions that occur by changing the number of Fermi points. Okay, so then what I'm going to do before I put interactions in, I'm going to draw a little sketch. It's not a phase diagram really, but it's a sketch that identifies these different situations. You can see a situation we have 4 Fermi points, 2, 4, 2, and 4 Fermi points with this opposite stuff. So I want to do a little drawing letting me know where I am. Let's see if I can do this roughly. I realize that my drawing abilities have gone really bad by being used to plotting the computer. So forgive me the quality of the drawing, but I'll try my best to make it clear. So the first thing that you ask yourself is here, like when I'm going to have these 4 Fermi points? I'm going to have these 4 Fermi points whenever the chemical potential is above the minimum. I'm going to call this band here band A and band B. Maybe, let me just check that my notation is the A and B is right. The other way around, I suspected that, yeah. I'm going to call this band A and band B. Band B and band A. So when do I have these 4 Fermi points? Well, I have these 4 Fermi points. I'm going to call that case 1. NF equals to 4, all positive. VF. I mean, of course, the VF changes, all positive Fermi velocities. When I'm going to have that? I'm going to have that when the chemical potential is above the minimum of band B. So in this case, band B has always a minimum at k equals to 0. So when mu is greater than EB0, I have these 4 Fermi points. So that's one case. OK, when that does happen? That happens. You can just compare mu with the minimum of the band. So I'm going to write down the expressions for the. You can diagonalize, of course, this 2 by 2 matrix, find the eigenvalues, and there are 2. And these 2 eigenvalues are written in terms of what I call, I'm going to write them down here, minus an effective magnetic field. So that's the usual 2-level solution, right? So 1 is where the effective field points, oops, the one is plus, the other one is minus. When the effective field, well, if you don't have a k dependence, but you have a local quantization axis, in this case, the effective field in k space, the spin orientation is changing with k, but locally is always aligned with the field, and in this case, is anti-aligned with the field. So by using that, what's the H effective? The H effective is just going to be the combination of the 2 components. I have a Zeeman field along the x direction, and I have a Zeeman field along the z direction, so the effective field is equal to that. How do I see this? Well, because my Ek, let's say Ek minus kt, can be written as k minus kt divided by 2m squared. This, of course, is going to be kt plus kt squared divided by 2m minus a term, which is going to be minus k kt over m. And, of course, the Ek plus kt is nothing but the same stuff. So it's going to be k plus kt squared divided by 2m plus kt divided by m. So my hz is essentially that term. So my hz of k is going to be just k times kt divided by m. So Vt times k. So it's a 2-level system in a Zeeman field, if you wish, that depends on momentum k. Okay, so the first region is going to be the region where mu is greater than EB0, and I have 4 Fermi points. And that's going to be happening if you just use the dispersion and the condition for mu, you get a curve, inequality, where the boundary, if I plot that as a function of hx over et, remind here that my hx has dimensions of energy, so I'm using funny units. It's not the real magnitude, it's energy, the same dimensions as E. So for that situation, you get a curve. This one is 1, this one is 0, and then the curve is mu over Et equals to 1 plus absolute value of hx over Et. So within this region here, I have NF equals to 4 Fermi points, and that's I call the region 1, corresponding to this case. But I can also have, I can do then the analysis, right? So if I'm in this situation, when am I going to have this case showing up? The second region here showing up? Well, I have to go below the bottom of this band and above either the minimum or the maximum. That's the place I have two regions. In this case, if hx over et is larger than 2, I'm OK. So the minimum happens at EB equals to 0. In case hx over et is less than 2, oops, the maximum, there's a maximum. The maximum happens at E0. So if I want to be in this case, where I have only 2 of those, there's piecewise conditions that I have to satisfy. OK, so then I'm going to just draw these things. Otherwise, I spend all my time just making these things. So you have another boundary here, u over et equals to 1 minus hx over et. There's another boundary. And so between those two lines, there's region 2. And I also put here a very crowded diagram, unfortunately. Let me try to change colors to see. So this is region 1. You have 4 Fermi points with all the velocities positive. And here's region 2. So I am in the case where the chemical potential is below the bottom of the upper band and above either the minimum or the maximum in this case. So that's the region 2. But the other regions, let me just put the numbers in the right place, 0. And then 2. This is minus 2, and this is 2. Those are the critical, the lines in which you change the shape of the lower band. So there's a region, what I'm going to call region 4. Region 4 is the region where your chemical potential falls below the minimum of those two bands. Okay. And so you get this out. And so the you have regions in which you have no Fermi points. These are regions we have 2 Fermi points. And this is the region that you have 4 Fermi points, but with the velocities being opposite. So the question is, depending where I am, my modes, my collective modes will look different. Okay? So what I'm going to do is now add the interactions. And as I predicted, then you see my backup plan, I think it would not work. I just prepared something because I was afraid. But so then, what I have to do now? Well, I have to ask myself, I have to put the interactions. So I have an idea about the Fermi points. I can linearize. And I can write down my Hamiltonian for the kinetic energy. So I'm going to do that. Up. Down. Yes.
If you have 4 Fermi points,
yeah.
That's also what you have in the absence of spin-orbit coupling.
Yes.
So the areas with 4 Fermi points is just a relabeling of the trivial situation of spin up and spin down without any coupling.
No. That's the point. And that's why I want to focus on that one. It's not the case. And the reason for that is that the Fermi velocities that you have in the problem, they will depend on the spin-orbit coupling value and on the hx value. So that will change, will create a dependence on the things. The additional thing is that the spin-orbit coupling and the Zeeman field or the Rabi fields will mix the spin and the charge degrees of freedom. So it's not going to have spin-charge separation. They'll be mixed. And they will mix in a special way. So you are right in the sense that, yeah, I can use the same technique. I'm going to bosonize. I'm going to find things. But the velocities will look very different. And the modes will be mixed modes between spin and charge. And they'll be helical. So it's different in that sense. Even in the 4 Fermi case, which is the standard case. That's why I want to talk about that even in the place that looks boring, is not so boring. There are interesting things that are happening.
But the dramatic situation is when you have 2 Fermi points, because then you have a strong mixing region between the 2 spins.
Yes.
Whereas when you have 4 Fermi points, you actually start out with only very weak mixtures of the opposite spin.
Yeah, and I agree. And it's very interesting to have to look at how you go from 4 to 2 also, because there's a topological phase transition. I'm just going to, for simplicity, I'm going to discuss something that's a bit more familiar, and I'll probably draw a phase diagram which encounters all the cases. Yeah, it's going to be more interesting. The more interesting cases are really the one you have 2 and the cases where the Fermi velocities are opposite, have opposite sign. Those are the most interesting cases also. But what I'm going to say is that even in the one that looks boring, it's actually not boring. There's something interesting that happens. And I want to point that out because it's the simplest case to treat in the 20 minutes that I have, right? 15? Whatever. So what I do then, as Wolfgang already pointed out, I have those 4 guys. I can play the same game of bosonization. So I play the same game. And so let me pick up whatever case, doesn't matter, as long as I have something either like this or like that, which is the simplest one that I'm going to, either this one or that one. I have 4 Fermi points. I can write down, my starting point, of course, is going to be writing down the kinetic energy in that eigenbasis. In that eigenbasis is just going to be the epsilon A and epsilon B, which I can linearize. So I'm going to just write down a linearized version so I don't spend too much time with it. So I can have, I'm going to call U alpha. Now it's a Fermi velocity in here for each one of those cases. Alpha labels A or B. And again, linearize son of Rk minus K mu alpha and A dagger R K alpha, AK alpha of R. So R again is right and left. I can still define right and left goers, just that the right and left goers do not have the same velocity anymore. And they have different quantum labels. Spin is no longer a good quantum number. It's an admixture of those spin states, which is k-dependent. And I can do the same game. Bosonize, blah, 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 because I bosonize in terms of these operators. So I'm just going to mention that briefly. So play the same trick. R, whatever, theta, sine of R, Q, rho alpha dagger, R, Q. So bosonize, again, sorry? Then convert this kinetic energy into a bosonic kinetic energy in this new in the eigenbasis. And that, of course, has very similar form as before. Sum over K A dagger K plus Q alpha R. Oh, sorry, I can just write down fully. It's going to be Q times U alpha times B dagger Q alpha B Q alpha. Okay, so the form looks exactly the same, but now in a different eigenbasis, in the eigenbasis, at the end of the day, of the eigenstates, Fermi eigenstates of this changed band dispersion. So then the next step is to say, okay, I have my interactions, which is the same interaction Hamiltonian that I had before. And the question is then, can I write it this Hamiltonian in the new basis? So the answer is yes. Why can you? Because you're going to now write your rows, or in terms of the fermion operators, in original fermion operators. But the original fermion operators are related by a momentum-dependent SU2 rotation that mixes the spin states. Right? So the Hamiltonian that I have, the quadratic stuff there, is a particle in a magnetic field-dependent, K-dependent magnetic field, two-level system. It's under SU2. I can do an SU2 rotation, and I'm mixing those spin-up and up states with some K-dependence. So I can rewrite that down then in terms of the fermions in the new basis, and I can write down this kinetic energy, this interaction energy in terms of the B's. Now, to interpret the things, I have to go back to the original basis because I have to find out how those things are related to each other to see what happens to spin-charge separation. So then I can play the same game, is that I can confine myself again to small momentum transfer processes, and I'm just going to jump to how I write this thing down. And I'm going to define not only k equals to 0. There's some linear term in Q, some vector contribution, which is bilinear, Gij, phi j, q, and this phi dagger vector. This Hamiltonian also is going to be bilinear on the BQ alphas. So the phi vector is going to be just my BQ alpha dagger, BQ beta, BQ A, B. Since I have 2 4 Fermi points. And this interaction matrix element is Gij is the interactions that you have between, for the scattering processes. And in this case, you're going to have something like 6 of the scattering processes for short momentum because you have 2 bands, now A and B. So A and B counts the label. You have G4. So you have 6 of them. In any case, this is quadratic, bilinear. In B's, in BQ alphas. You can play the same game, diagonalize, and get a Bogoliubov type of Hamiltonian, which has 2 modes in this case. Plus some reference energy. The big difference now is that this Vm is going to be a function of spin-orbit coupling, Hx, the interaction, and so on. And you're going to have 2 modes in this case because essentially you have 4 Fermi points. If you cross here, you would have only a single mode, strongly mixed, as I already pointed out. We can get some analytic expressions for this velocity. It's very complicated. I don't want to go. I want to just make a drawing because in any case, I might be running out of time. And the drawing that I want to do is just showing the following. I want to bring that phase diagram down a little bit. So descente, montée, descente. No, so number 1 maybe. I'm going to stop here at some point. Okay. And so if I'm somewhere in the first region, 1, on the top with the chemical potential over there, you can see as I change Hx, I can go from the place where I have 4 Fermi points to 2 Fermi points, which was the question that Wolfgang had. So what happens there, right? So what I'm going to do is to show that you have 2 modes, and I'm going to be plotting the schematically, unfortunately, so with not too many numbers, what those 2 modes do. So this is going to be the velocity of the modes with respect to t, and that's Hx with respect to Et, the transfer, energy transfer. And this is the place where this is 0. And these lines that I drew here at some position Hx, it depends on the numbers, are the lines corresponding to crossing from region 1 to region 2. So you have a lower mode. You have a lower mode that at that point, the point when you cross from 4 Fermi points to 2 Fermi points will disappear. That's going to be, in this configuration, sort of a more spin-rich type of mode. Clearly, when Hx equals to 0, what happens? Exactly at Hx equals to 0. If Hx is exactly equal to 0, I have no Zeeman field. Well, I shifted the band to the right and to the left. Can this momentum be gauged away? Yes, it can. It's irrelevant. So this point of hx equals to 0, here, right here, this mode at hx equals 0 corresponds to a purely spin density mode. And there's another one with higher energy, doing something like this, which exactly at 8 equals to 0 corresponds to the charge density mode. Exactly at hx equals to 0, kT is irrelevant, can be gauged away, and you recover exactly the results from spin charge separation. So you have spin charge separation precisely at hx equals to 0, irrespective of what kT is, because it can be absorbed. You just shift the momentum. This isn't two independent bands. They don't know that they were shifted. Now, the important point is that only one mode survives. Both modes are, as soon as you move away from hx equals 0 with a finite kT, they're mixed. And they get strongly mixed. So at some point, when hx becomes sufficiently large, the lower energy mode gets suppressed, which is the one that's sort of more or less spin-rich kind of. And then the other mode survives. And at the transition point, the velocity changes slope. There's a kink, slows down a little bit. So there's a kink in the velocity as you go from the phase with nf equals to 4 to nf equals to 2. So you lose one mode where the velocity goes all the way down to 0, and the new mode that emerges develops a kink in the velocity. Okay, just to finalize, then I want to say, well, okay, you said something like this, and then, so those modes are mixed. One interesting thing about that is that these modes here are helical. So if you look at the structure of those guys, let's say in real space, for Q positive, these particles are doing something like that, for Q positive. And for Q negative, they have opposite, I don't know if I can draw that, opposite helicity. So I would say those are bosons that arise, both of them are bosons, but they have a built-in helicity which comes along from the fact that the spin-orbit coupling is already inducing some helicity on the fermions. So these are those are massless bosons and helical. So I call that helical bosons, whatever, but some people may want to call that wild bosons. I don't know if it's a legitimate thing to say. It maybe confuse people. But they're helical. And at the borderline, there's a transition. The sound velocity changes discontinuously when I go from one mode to the other. And just to finalize, I think, Ivan, I have 5 more minutes or something like this, yeah? I want to say, well, if you say something about that, what happens, how you see those things? How can you even see if those things are really helical? How do you detect that? I don't know if this can be done, but maybe it's a question even for Wolfgang. So what we want to do then is, in order to see that kind of stuff, one thing that I can think of is to try to measure the structure factor tensor. And by structure factor tensor, I mean correlations between density if you have, and density and spin operators. So I can compute them here also analytically, some S, because you can relate the bosons, these bosons here, to what operators? To the density operators and to the spin operators that I had initially. And since I know what the eigenstates of these guys are, if I know how to represent the D's in terms of the spin density in the original basis and the charge density in the original basis, I can compute those correlation functions. Okay, so the correlation functions that I want to look at, I just want to point that out because I think if it's possible to measure them, that will be an interesting thing with all the caveats. At some point, it's possible to measure them. So, tableau there. So the thing that I want to then look at is the structure factor, or structure factor tensor, which I can write in the Cullen-Lehmann representation, spectral representation, as a sum over the, analyzing the ground state of the operators, OI, P, whatever, MP, OJ, Q minus P, or Q, I'm sorry. That's the Q. Evolved. Time already Fourier transformed. In terms of the eigenstates, it's energy reference, doesn't matter. But these OIs can be the density, it can be the density operator. So the OI Q involves the density, and then the spin, whatever, Z, X, Y, or X, Y, Z, depends whatever order you want to put them. Or sigma Z and sigma plus, sigma minus Q. So these correlators, of course, since I can relate my bosons to these density operators, I have to do a transformation that's required, but I can relate them. I can compute this spectral function. And so all components of the tensor. So let me just, in the rho case, if you just look at the rho correlations, I'll just make a sketch, very rough sketch. You can see this is a function of Q. You can see two modes dispersing. I don't know if I can do the peaks, but the peaks, just for the right one, they disperse. So if you can measure the rho correlation function, you're going to see that there are poles precisely at the location of the velocities that one calculate. So you see that. Okay, great. And then you can say, well, you can also measure sigma sigma. In this case, maybe sigma z or something like this. And you see the same thing. You see some structure, and again, two velocities dispersing some peaks, and so on. So if you can measure either one of them, you can at least identify there are two modes, and you can say how much spectral weight they carry in the density channel, how much spectral weight they carry in the sigma z channel. But what's more interesting for me is if I can calculate, if I can measure correlations between sigma plus rho and sigma plus, sigma minus. And the reason for that is that if my system is chiral helical, the response is going to be different. If they are not, the response is going to be the same. So if I do that for spin orbit, without spin orbit coupling at all, what do I get? I get two modes, yes, in that case. Those two modes have now different velocities, right? And I have only a response in the charge channel or the spin-spin channel, separated. Each one has their own mode. But here, they're coupled. So I can identify any measurement that I do of any correlation function, I see those two modes, except in the limit there's no spin-orbit coupling when the spin and charge are completely separated. Otherwise, they're always mixed. So if I could measure that, rho sigma plus sigma minus correlation, and they're different, right, I have measured the helicity. Or have a measure of the helicity. I mean, the better way is just to compute sigma p, sigma dot p, which is, I don't know if it's easier to measure. But if I can measure this correlator, and I have spin-orbit coupling, these responses will be different. Automatically, there is some helical contribution coming up, and then you should be able. You see the same things. You see peaks of the two velocities here for that particular case one. But if those things are different, I can measure the helicity if I have enough sensitivity. So again, it's all in the realm of dreams, right? I'm all dreaming here. So then maybe I'll just say, I'm out of time now, right? Is it over? I'll just say SU3. No, just 30 seconds. Because I said it's SU2, SUN, so I thought that my theorem applies, as you see. It's like the backup plan, only one thing, and you never know. You always go too slow. Psychological, yeah, right. So now the question is, can you play the same game with SU3? Okay, yeah, but why do you want to do that? It's so much more complicated. And maybe I won't review it. It's an open question. I won't review everything, but there's one interesting aspect once you go to SU3, that once you go to SU3, you spin-orbit coupling, you have 3 internal states. The easiest way to introduce the spin-orbit coupling already takes you out of SO3. It takes you out of the angular momentum algebra, which means that the modes that you're going to have are not going to be only a mixture of charge and spin degrees of freedom. There's something else. And what can you guess is that something else that should arise? If I have angular momentum algebra, I have my J for spin matrices for 1, appearing my kinetic energy Hamiltonian, and I have to show up something else. What's that something else? Something else has a tensor structure in the spin. So for the SU3 case, that's an open question, right? If you have spin-orbit coupling, you're going to have, you can play the same game because you can linearize, you can rotate that into some, do an SU3 rotation, and you're going to have more complication. At the end of the day, you're going to have bilinears again, it's the same game. However, the structure of the bosons will lie beyond SU2, beyond SO3, because SO3, SO2 is isomorphic, right? The spin 1 case, or pseudo-spin 1 case, is just a higher representation of SU2. You need to involve some Gell-Mann stuff to come in. And that means you're going to have quadrupolar correlations. So those things would arise in the SU3 case. And that, of course, complicates your life, but if you want to look for some additional bosons or collective excitations which are more bizarre, certainly those ones will be more bizarre. Because they're not only a mixture of spin and charge, they're a mixture of spin and charge and this quadrupolar term, SX, SY, or SZ square, whatever. You're going to have a quadrupolar spin terms. And I'll end up here. So that's what, for me, a big open question. What's the structure of these bosonic particles that emerge in the SU3 case? Okay. Thank you.